Okay, we are in chapter 8, second section, and now day 2. You really don't need to write this down. What I'd like to do is show you an interesting application, so a way that using exponents is applied in the real world. And this is called a fractal tree. If you want, you could put a little diagram of what a fractal tree looks like. Why don't you do that? You don't have to write all the words, but a fractal tree is something you can construct. And it looks like a little tree. And one would begin with a single line segment, and that would be considered step 0. So you need kind of a trunk for the tree. And that's 1 unit long. And then we could take this through the process of developing branches on the tree. So each time we make a step, so step 1, we are adding 3 shorter segments that are half of the measure of the trunk. Okay, so step 1, each of these little branches, 3 branches, are half of the previous steps. Shortest branches, I guess you would say. When we go to step 2, each of the 3 branches from step 1 now has 3 branches on the end of it, see that? That are half as long as step 1's branches. And we could go on forever. Here's step 3. Step 3, again, each of the branches from step 2 now has 3 little branches that are half a unit, half of the previous little branches we saw in length. Okay? So that's how you form a fractal tree. We just continue to add successively shorter branches. Each new set of branches half the length of the old. So the book goes on to ask us to make a table to show how many new branches would be at any step. One way to find the number of branches at a step would be to take the tree and keep taking it step by step to the number of steps you are trying to get to. But if I wanted to find out how many branches were in step 20, that would take a lot of drawing fractal branches, right? And so could we find a pattern in this that would help us do that mathematically and not have to draw this out? So the second thing that they do for you is oh no, they don't do it yet. In the solution they do this. Their first question is, write the number of new branches as a power of 3. So let's do this. Let's make a little table, which is what they do. So if we put here the step we're on, and then the number of branches, we're going to look for some kind of a relationship here. And so the step 0 has how many branches? It looks like 1, right? Step 1 has how many branches? 1, 2, 3, so 3. Step 2 has how many branches? 3, 6, 9, right? 9. Step 3 has how many branches? How many is that? Say it. 27. Okay, so when we look at the number of branches there, how can we write these as powers of 3? So look, do you see that they are powers of 3? So we could say like 27 equals 3 to the what power? 3 to the 3rd. And which step do we find 27 branches at? You see this? The 3rd step. So at the 3rd step, we have 3 to the 3rd. At the 2nd step, we have 3 to the what? 2nd. At the 1st step, we have 3 to the first. And at the 0 step, we have 3 to the what? 3 to the 0. Good. So 3 to the 0 equals 1. Okay? So if I wanted to know how many branches were in step 20, how would I find it?
3 to the 20.
3 to the 20, which I wouldn't want to do by hand. I'd probably rather have a calculator to find that, right? Okay. How many times greater is the number of new branches added at step 5 than the number of new branches added at step 2? That's an interesting question. Do we know how many new branches were added at step 2? How many? Right here. 3 to the 2nd, right? And so how many new branches would be added at step 5? Let's go down and predict. Step 5 would be how many new branches? Everyone say it. 3 to the 5th. So if we're going to find out how many more branches were added at step 5 than step 3, how do we do that? We went from 3 to the 2nd. How many times greater is step 5? So we went from 3 to the 2nd at step 2. And we have to times it by something to get to step 5. What would you times 3 squared by? Wake up and look. What would you times 3 squared by to get to 3 to the 5th? You all can do that. It would be 3, 2, 1. 3 to the 3rd. You can see you're just applying your product of powers property. You're multiplying powers, aren't you? If you didn't remember how to do it, you could use your inverse operations, right? And you could just divide, and there it is, 3 to the 3rd that way as well. Okay? So that's a fractal tree in case that comes up in your assignment. See if you can answer this question and come back when. Okay, so we have step 0, we have 1 branch. And what's the length of that branch? What is it? They said it was 1. Okay, at step 1, we have how many branches? Again, we have 3, and that was based on 3 to the 1st, right? And how long are the branches? How long compared to step 0? They are 1/2. They're half of 1, which is a half. Okay? Step 2, how many branches? 3 to the 2nd, right, which was 9. That doesn't really matter anymore, but I'm just keeping this table complete. And how long is a branch now? 1/4. How did you find that? Okay, so half of 1/2. Half times half is 1/4. This is half times half, right? Okay, let's look at step 3, because we're supposed to find how long a branch is at step 9. We could keep creating it by making the table if we don't know the math, right? How many branches in step 3? We said there were 27. And now, if step 2 has branches that are 1/4 long, how long is step 3's branches? So what did you just multiply by? Oops. I'm writing what we multiplied by. 1/8. Because 1/8 is really half times a half times a half. How many factors of 2 are now in the denominator? Here. This is 1/2 to the 3rd, right? This one here is 1/2 to the what? 2nd. Step 2 is 1/2 to the 2nd. See that? Step 3 is 1/2 to the 3rd. We could actually put the whole 1/2 to the 3rd because the 1 in the numerator is just 1 no matter what the power, right? Okay? So, and in the very first step, we simply have 1/2 the whole thing to the 1st. Actually, when we look at the length of step 0, what do we have? 1/2 to the what? To the 0. So we're using the exponents here just as we were in finding the number of branches, right? All we need to know is the step, so we can imagine going all the way to step 9, and how long will the branches be? Say it. 1/2 to the 9th, which is 1/2 to the 9th. And what is 2 to the 9th? 512. So they're 1/512th unit long. Good job. Isn't that neat? That's using your properties of exponents in a real application. Here's another way we can use the properties. We talked about magnitude, and here's a question on magnitude. It seems that we're always talking about astronomy when we're talking magnitude because there's a great distance between astronomical things, and also stars and things like that put off great amounts of energy in many cases, right? This says that the luminosity in watts of a star is the total amount of energy emitted from the star per unit time. So the more energy per second is a greater luminosity, right? Less energy released per second is a lower luminosity. More energy released per second is a greater luminosity. So that's brightness, okay? So the order of magnitude of the luminosity of the sun is 10 to the 26 watts. How many zeros does that have? 26. That's a big number right there, big power of 10. And the star Canopus is one of the brightest stars in our sky that we can see from Earth. The order of magnitude of luminosity of Canopus is 10 to the 30 watts. So it's further away, so we don't quite have as much of its light like we do the sun, right? But it is amazingly powerful. How many more times more luminous is Canopus than the sun? How many more times more luminous is that star than the sun? So you're really just comparing 10 to the 30th and 10 to the 26th, right? And it's really a very easy question. As hard as some of these words are, it's really a very easy question, isn't it? We're basically saying, here's the sun, 10 to the 26th. What would I have to multiply it to? Times what? To get to 10 to the 30th. And the answer is 10 to the 4th power, which is simply what number? 10,000. That's it. It's 10. That star is 10,000 times more luminous than the sun. 10,000 feels like such a small number when we're looking at these powers of 10, right? But imagine a star being 10,000 times more powerful. That's a lot, isn't it? Even twice as powerful is a big deal. 10,000 times? It's amazing. Okay, so don't be afraid of these tough words. You're applying your properties in today's assignment.